Okay. Today we are going to discuss something related with the steel structure or steel basics, we can say. See, we all are going to learn the design analysis in detail in upcoming sessions. As for different sector knowledge, we can say steel sector, water sector, and RCC sector, high-rise building. Here, actually, our first month aim was to develop the understanding in general. Okay, and that's why whatever training I'm giving you, it is with some, we can say, very approximate, and we can say very basic level, just to develop the perspective and understanding overall, so that you can take decisions or you can understand the detailed analysis and design concepts. Whenever we read any book, before reading any book, actually basics should be clear, and that is why we are here. Whatever we have learned till now is the intention was only to understand the detailed things in totality and develop a common sense which is required to take decisions. Now, today we will start with the steel basics. Steel means I am saying mild steel. So, which we generally use in industrial structures in general, where we are using mild steel. What is the grade of mild steel?
250.
So, yes, 250 Newton per mm square. So, whenever we use this steel, then how to handle this? Generally, we use IS 800 for design of this steel. So let me first, all of you know whatever we, I think, last time discussed only. So the stress strain graph. So generally, this is the stress strain graph of mild steel, where we get exact yield point here, and the stress corresponding to yield point is 250. So this is your graph sigma, that is stress. So this is your Fy here at this point, yield point. But all of you know that we don't design the structure for yield stress. Rather, we give factor of safety. So there are different factor of safety for different stresses. So if it is axial stress, sigma A in tension, then permissible stress in tension is, as per code, point, how much? Anybody knows this? So this is, as per code, it is 0.6 Fy. So definitely the here it will come somewhere here, 0.6 Fy. Then bending stress. Okay, so sigma B T, bending tension generally. The permissible stress is 0.66 Fy. Okay. So if it Fy is 250, what will be this value? Yes. 150 Newton per mm square. This is permissible stress in tension. So if any steel member which is in purely axial tension, then we can say we can take this stress value for the design. And if it is a bending member like beams, then you can take 0.66 Fy. This is nothing but 165, na, I think. Are you getting all of you?
Yes, sir.
Okay. Now let's take one simple example. Last time we have taken, just discuss this again. Let's say we have a rod like this. And let's say this rod is having diameter as 16 mm. and this is a mild steel rod, mild steel. Okay, circular rod. So if I ask you how much maximum tension this rod can take, can anybody tell me how much maximum tension it can take? Maximum or design tension, we can say. Yes. Hello.
Yes, sir. 0.6 Fy by area.
Yes. So we can say stress, rather force is nothing but stress into area, that everybody knows. Stress into area, and we know the permissible stresses, because if I want the permissible force, so I'm asking you what is the permissible tension it can take, this rod can take. So whatever permissible force you are interested in, you can calculate by multiplying the permissible stress and area, right? So permissible stress is 0.6 Fy in axial tension. So all of you know this is axial tension, pure axial tension, pure axial tension into area. So zero point 0.6 into Fy is 250, and area of the bar is pi by 4 into 16 square. So it will be something near about 150 into 200. So how much will this be? Newton. That means 30 kilonewton, isn't it? So this can take tension 30 kilonewton maximum. Okay, getting this.
Yes, sir.
And the next problem similar, but I'm asking you, the force is given and we have to check whether whatever rod you have provided, whether it is safe or not. Okay, so let's say we have a rod and we have a tension, say here, uh, the diameter of this rod is 20 mm diameter. Okay, and the force applied there is say 70 kilonewton. So if the force is 70 kilonewton, the rod diameter is this much, then is it safe? Okay, so is it safe is our question. And this is mild steel bar, mild steel. Okay, so generally all of you know that phi term is used for mild steel diameter and tor is used for tor steel. Okay, so please try to understand, phi is generally used for mild steel, which is a plain bar, and this tor is used for high strength bars, deform bars, HYSD, which we use in RCC structures, and this we use in mild industrial structures or mild steel. Now tell me, can this take this bar force? Can this bar take the force? How can we check this whether it is safe or not? So due to this force, what this is nothing but a tension force, and this will create stress in the bar. So what is the stress? Actual stress, actual tensile stress, sigma 80. So generally, whenever we calculate actual, we call it as a sigma 80 cal. Cal means calculated. Tension upon area. So what is the tension? 70 kilonewton. So we need to say convert that into Newton, and area of the bar is pi by 4 into 20 square. So how much this number will come roughly? So it will be 314. कितना है गई? I don't know, but it will be something near to this. So is it safe? Is it safe or not?
Yes, it is safe because it is less than 250.
No. See, this is not safe because permissible stress कितना है हमारा? 0.6 FY. So 0.6 FY, that is 0.6 into 250, which is 150 Newton, and therefore it is not safe because it is more than 150 Newton per mm square. Not safe, right? So now it is not safe. So what you will do if you want to make it safe? क्या करोगे आप? What you will do if you want to reduce this value? You want to
Increase diameter.
Yeah, so increase the area. So once you increase, because this is in the denominator, if you increase the area, then the stress will reduce. So you can try either 25 mm diameter of bar or 32, whatever means comfortable, and then you can check the stress, and if it is less than 150, then it would be okay. So this is the design of we can say bars in tension. So such kind of case comes in trusses also. So if I ask you, there is a truss, let's say, so there can be truss, and in truss, all of you know that truss is a so whatever members are there in the trusses, they all are axial force members. So there is no bending in the truss. So generally this is the case. And okay. So let's say this is your truss. And we have all, let's say this truss is supported on some columns. In industry, we see such kind of trusses. And there may be forces in the truss. So it may be tension, then it may be compression in the member, then it may be tension like this. Okay. So the member is having tension. So if you want to design this, let's say this member is in tension, and if you want to design this, first of all, you get the forces in the members through analysis, either software analysis or manual calculations. So let's say the tension in this bar is, let's say, maybe 10 kilonewton. Okay. In this member. So once you know the tension, how can you design the member? Let's say if I ask you, this is a truss. I have analyzed the truss for vertical loads, whatever are there as per code. And then I got the tension in this member, this diagonal member, as 10 kilonewton. Okay. And I'm asking you design this member. And design this member using, let's say, angle section. Okay. Use angle section. So how can you design, please?
We will choose one angle section from IS 800.
Yes.
And then select means area, then tension divided by area.
Actual stress. So say choose one angle, or assume, or we can say assume one angle section. Then once you assume the angle section, then calculate the area. Not calculate the area, get the area from table, steel table. From steel table. So once you get the area, now you know the tension from the analysis. Now you can calculate the stresses, axial tension, as it is a tension force here in this bar. So calculate it. Sigma 80 calculated is nothing but T upon area. Then you will get some stress in Newton per mm square. And as it is an axial tension member, the stress value, whatever you get, should be less than how much? Permissible stress in 0.6 Fy, which is nothing but 150 Newton per mm square. If it is less than this, then it is safe. If it is more than 150, what you will do? You will choose higher section with higher area, right? Isn't it? Now let's try one angle from steel table. So they actually steel table IS 808 actually. This is a steel table we have. IS 800 is for say stress calculation permissible stresses, which is required for the design, and this is a steel table actually. IS 808 is a steel table. So let's say if we have one angle here like this, and then you can choose any of the angle, because see, in the beginning you don't know. So now there are a lot of angles given in this table. So 20 by 3, 20 by 4, 25, 35, 45, and lot of angles are there till 100, 200 tak hai. So till 200. But how will you choose where to start? Yes, any idea? If you want to choose any angle section, how will you choose?
No idea, sir.
Yeah, actually, see, what can we do in the tension member is a simple design. We can do, you know, this equation. Calculated stress, actual stress is nothing but tension upon area. So we can reverse that. So what is the area required? So if area required is nothing but tension upon sigma AT, you can take permissible stress. Okay.
Yes.
Better way, we are reversing the things. What is the area required? So we have already done that, isn't it, in this rod? So actually you were knowing this actually. If you don't know, then you can divide that by permissible stress. So what is the tension? 20 है ना? कितना है? 10 है, sorry. 10 है, हाँ. So 10 kilonewton and divide by permissible stress. See, try to understand the stresses in a very simple manner actually, because our whole structural engineering is design is based on the stresses and permissible stresses. Actual stress, permissible stress. Okay. So we are dealing with the area required. We are dealing with the, we can say, moment of inertia required or Z required, like that. So that's why stresses, actual stresses and permissible stresses, that is the design, nothing else. So we calculate the actual stresses and we compare that with the permissible stresses. Actual stress should be less than permissible stress. This is whole design philosophy. Nothing is different. So please try to understand the stresses in detail, maximum possible. Now sigma 80 permissible, all of you know it is 0.6 Fy, which is nothing but 150. So 10 into 10 raised to 3 150. कितना आएगा ये? Area required
66 mm square.
66 mm square. I have not calculated. Okay, let's assume this area required is this. So if you provide area more than 66, isn't it? Then it will be safe. It should be safe, isn't it? Now you can go in the table. And here, these are the angles 20 by 20 by 3. So we want 66. Now see, the steel table gives the area in cm square. So let's convert that in cm square. So cm square कितना आएगा इसका? Yes.
0.66.
10 raised to minus 2. Right?
Yes.
Go into the table. So it seems that our minimum say cross section is sufficient actually, isn't it? So see, 20 by 20 by 3 is having 1.12 and our required area is 0.6, right? So which is very less. Getting?
Yes, sir.
Okay, so whenever you get minimum forces in the trusses, actually this may not be the case in general, but okay. So that means you can see this, if you choose even this areas 20 by 20 by 3 for the design, it will be okay. But generally, whenever we do design steel structures, we deal with thicknesses more than 4 mm actually. You can choose this 4 mm because for durability and corrosion resistance, it is better to have a member thickness 4 mm and more, 4 mm, 5 mm like this. So you can choose any of these sections. And so this will be your choice. So how we are doing, it is very easy to check, isn't it? Let's say you are choosing 20 by 20 by 4 mm. So what is the area? 1.45 cm square, this much. So you can again calculate the then sigma AT calculated. So let's say try 20 by 20 by 4 mm angle. So the area of this angle is how much?
1.45.
It was 1.45, right? So 1.45. 1.45 cm square, that means 145 mm square. So what is the actual stress? Force upon area. So T upon A provided. So T is 10 into 10 raised to 3 divided by area provided is 145. So how much is the stress?
69.
69 Newton per mm square. Okay, which is less than 150. Right? Okay.
Yes, sir.
Yes.
So whenever you get any axial tension member, actually, they are generally in the trusses. Either it may be truss or it may be like suspended rods, suspended cables, and it may be even bottom cord of the tension truss. So all of you know that this bottom cord is in tension. So these all members are in tension. Or there are some diagonals which may go in tension. Some may go in compression also. So you get that from the analysis. And you have to design. So you can choose any section. It may be either angle or square rod, circular rod, or channels, or whatever section you use. We have to deal with only areas. So that is very simple design. In steel structures, tension member design is the simplest design. So this is with respect to the tension member. So if you want to design, this is the only, choose some member, then check the get the area and calculate the actual stress and compare with the permissible stress. That's it. So this is the tension member design. Now the problem comes when the member goes in compression. So this was our tension member design, we can say. So we were dealing here with the tension member design. Now let's deal with the compression member. So the steel member is steel member. Let's say this is a square rod of steel like this. Okay. Mild steel. We are dealing with mild steel only, MS bar. And let's say it is having one compressive force here. Okay. Now what will happen to this rod? So there will be, what will happen to this? Please tell me. Due to the compression, what will happen?
This will buckle.
Yeah. So buckle means first of all there will be stress actually in this. So due to the compression there will be stress compression upon area, right? So all of you know that this is having some area, this is having some area, and so there will be axial compressive stress, AC I am taking, and this is nothing but C upon area. So compressive stress will be there in Newton per mm square. So once you start increasing the load, so actually, and what will be the permissible stress? Permissible stress kitna rahega? As it is a,
0.668.
so permissible stress maximum, it is something near to 0.6, near to I'm saying, because this is a steel material. So I can say it will be near to 150. I'm just giving this example. Permissible stress in compression, axial compression. Now, but you will see that once you increase the compressive force slowly, let's say first it was 10 kilonewton, then you started with 20 kilonewton, then 30 kilonewton. So as you increase the compressive force at one moment of time, what will happen to this? Let's say I'm just having this restraint. So if you go and increasing, so at one moment of time, what will happen? This will buckle actually. It will directly buckle. Even though due to the compression, it will buckle like this. So this is nothing but buckling of the rod arm. And as it is buckling, it may happen that even though, let's say, even though the bar is having capacity, full capacity, let's say this bar is having capacity of 60 kilonewton. In tension, I'm saying this bar is having capacity in tension as 60 kilonewton. But due to buckling, what is happening? It will buckle, let's say, at 30 kilonewton force itself. That means even though this raw material is having capacity of 60 kilonewton, it could not reach its capacity because it failed at 30 kilonewton force. So failed due to buckling. Are you getting? Are you getting what I'm trying to say? So due to the compression, all of you know that it buckles. And let's say this rod is having capacity of 60 kilonewton, but due to buckling, it has failed at 30 kilonewton only. So if I ask you, what is the capacity of this rod? Compression capacity. What is the capacity of this rod then? If I ask
30
you.
kilonewton.
So this is your capacity actually. Because after that, it is failing due to buckling. So this is your capacity. That means you can say that even this is the maximum capacity of steel, let's say, maximum capacity in tension, let's say, because it is a steel material. Generally, steel material is strong in compression and tension. The values are same. Here you can see, okay, near to this. 150 is in tension, compression also, but maximum capacity. But in compression, what happens? There is a tendency of buckling, and due to buckling, it buckles early than the maximum capacity reach. So we can say the capacity is governed by not only this permissible stress, but it is governed by something else, which is nothing but buckling. So our compression member is governed by buckling criteria. So whatever permissible stresses are there, sigma AC permissible, they depend on, so this is not your value in design. Don't take this. This is maximum value you can take, but it depends on buckling. And definitely it will be less than this, because you know that, let's say this is the maximum capacity corresponding to 150 Newton per mm square, which is this. And you know that this is something, abhi ye 50% ho gaya, matlab 75 Newton per mm square. That means you can say that this sigma AC permissible is always less than tension capacity. So it is less than tension capacity and depends on the buckling. So as your buckling is more, then this value will be less. Yes or no? So the permissible value will be less if the buckling is more. Getting this? Hello?
Yes, sir.
Yes, sir.
Yeah. Now I'm asking you questions that, let's say we have a square rod. So first case is that you are having this square rod of the same dimension. Then second case is that you are having this rod, and then third case is that the cross section of the each rod is same. It is not different. Okay. ये same ही है समझो. So the size is same for all the rods, 3 rods. You can assume any size, let's say 100 by 100 or something, whatever. All are 100 by 100. That means cross-sectional area is same. And let's say we have a compressive force here as 10 kilonewton, let's say. Or let's say, shall we take see, in steel actually 100 by 100 is a quite big number. So better way, let me assume this. (50 by 50), let's say. Okay. All are 50 by 50 mm areas. And let's say we have a compressive force of, let's say 50 kilonewton. So all these square rods are having the same compressive force. And this is also 50 kilonewton. Now, if I ask you which bar is having more capacity, first one, second one, or third one, which will have more capacity?
First one, sir.
This will have more capacity. Why?
Length is less, so buckling effect will be less for that
Yeah,
one.
so this will not buckle earlier. So, and as it is very long, it will buckle earlier. That means we can say that the buckling depends on length. So one of the important criteria is length. So L1, then this is, let's say, L2, and let's say this is our L3. So as the length increases, the buckling will be more, and due to that, the capacity of this third bar will be less, and this will be. So this is one of the criteria of buckling first. Okay. So buckling depends on the length. If the length is more, capacity is less. If the length is less, capacity is more for the same forces and cross-sectional area. Now, one more problem. Let's take all the lengths are same. Okay, so this is first case. Then let's say this is your second case, and let's say this is your third case. We have a compression, same force, let's say 10 kilonewton or whatever you assume. Force is same on all the columns. As it is a compression, you know that we can say it as a column member. Column is a compression member generally. So forces are same, but the cross-sectional area is more here in third case. Tell me which column is having more capacity.
Third one.
Third one. So this will have more capacity.
Yes, sir.
Because the area is more, but there is one more term which is related with the capacity, which is related with the buckling parameter. That is nothing but R. So area more, and I would say there is a effective important term that is nothing but R is more. What is R?
Radius of gyration.
So radius of gyration. Is more. And what is R value actually? In this is nothing but root I upon A. So that means if you have R more, then your capacity will be more, isn't it? Okay. So if you provide any section of which R is more, right, then the capacity will be more for that section. For example, let's go here. Instead of, let's choose channel section. Okay, so we have a channel, let's say. I'm asking you if you are using the channel section for compression member as a compression member. So here you can see the in steel table we have the weight given, mass, that is kg per meter. So weight of this member per meter for channels MC 75, MC 100. We have a cross sectional area given in cm square. MC 100 is 12.2 cm square. Then D means depth of beam, B means width of channel, then thickness of web, thickness of flange. Everything is given here. And here you will see there are other parameters like Ix means moment of inertia about x-axis, Ix. Then Iy means moment of inertia about y-axis, Iy. And there is Rx and Ry. And this Rx and Ry means radius of gyrations. Okay.
Yes, sir.
Now here you can see here Rx is something for channel MC75, let's say. Rx is 2.94 and Ry is 1.19. So any cross section is having two radius of gyration, one about x-axis, one about y-axis. And whenever we design it, it is governed by the minimum radius of gyration. Okay. So let's see what I mean to say by this. So this is understood. R is nothing but I upon Y. Now, if I ask you one question that let's say we have one scale and the dimensions of scales are like this. ये है ऐसे scale है कुछ तो. So this is your plan. And this is your side elevation. Okay. Let's say this scale is having dimension. Let's say this is 10 mm and this dimension is 100 mm. So so this is your side view, let's say. Side view, and this is your front view. This is same, both members are same, huh? Only views are different. Front view, and the dimension of the scale is in plan. If you see the plan, then this is your 10 mm and this is your 100 mm. So let's say we have a scale or strip of the steel, and now if I apply a force, compressive force over here like this, this strip is same actually, no problem. Now if I apply the compressive force, how will it buckle? So the compressive force, let's choose 10 kilonewton. See, both rods are not separate, they are same. Or it would be better if I draw it 3D, then it would be. समझे ऐसे है हमारी strip. Let's draw it 3D, then it would be easier to. And let's say you are applying a force over here. This dimension is 10 mm and this dimension is 100 mm. Okay. So if you apply the compression force, how will it buckle? So this is your 3D and this is your front view. Side view this is, and this is front view. How will it buckle? Tell me. कैसे buckle होगा ये? Will it buckle like this? First, how will it buckle? Will it buckle like this? Yes or no? In the beginning, how will it buckle? As you go on increasing the compressive force, how will it buckle? Will it buckle like this or will it buckle like this first? कैसे करेगा? Buckling कैसे होगा? You can take an example of your scale, whatever you use, plastic scale or steel scale, whatever you use. We use it for drawing purpose, right? So if you apply this force, who will this buckle first like this or first like this? Hello?
Yes, sir.
कैसे बकल होगा ये? फर्स्ट केस बकल फर्स्ट होगी या सेकंड वाली फर्स्ट होगी? कौन होगा बकल फर्स्ट? You can take you can give the compressive force to the, let's say, plastic or steel scale. We use it for drawing purpose. Feet inch scale, all of you know that 30 mm 300 mm scale.
Yes, sir.
पता है ना?
Yes,
उसको
sir.
अगर compressive force ऐसे लगाए तो कैसे बकल होगी? पहले ऐसे बकल होगी या ऐसे फर्स्ट हो केस की तरह? How will it buckle?
The second one.
Are you sure?
Yes, sir.
ऐसे ऐसे बकल होगा पहले या ऐसे बकल होगा? ये स्केल है समझो ना. और आप यू आर अप्लाइंग फोर्स लाइक दिस compressive force here.
The
You are
second
just
one
push.
कितना buckle होगा, sir?
ऐसे बकल होगा? Are you sure?
I think first answer.
फर्स्ट होगा ना. थिन है ना ये मेंबर, थिन साइड में ज्यादा होगा ना बकल फास्ट.
हाँ, yes, sir. Thin side में.
स्किल ले लो ना, स्केल ले लो और प्रेस करो. कैसे बकल होने वाली है? ऐसे ही बकल होगी ना, स्ट्रिप्स.
Yes, sir.
So this will buckle first. That means you know that if this dimension is less, then it will buckle in that direction. So I can say, let's say this is your YY and let's say this is your XX. So it is buckling in about the y-axis, right? About y-axis it is buckling, correct?
Yes, sir.
Why it is buckling about y-axis? Because its dimension is less, 10 mm, isn't it? That means I can say about y-axis, that means RYY is less, okay, is less. And RYY, RXX is more. Are you getting? Yes.
Yes, sir.
And we can verify that by calculation also. Let's calculate RXX first. So let's, RXX means what? Root I upon A. Now as we are calculating RXX, it should be IXX, right? Now batao. Now let's calculate for this. Our size of the say this strip is scale is 10 mm by 100 mm. Okay. So root IX कितना आएगा? BD cube. What is B? We are calculating IXX. So whenever we calculate IXX, B is this. Yes or no? ये है ना. अभी let's say we are calculating. This is your X and this is your Y. So whenever I calculate IXX, this will be my D. Yes or no? And this will be my B. So BD cube. So how much is this? 10. B D is how much? 100 cube divided by 12. So this is your I, and area is simple, 10 into 100. So what will be this value? कितना आएगी? 29 mm roughly. Okay. Now, if you want to calculate RYY, then it will be root IY upon area. So what is IY? IY is nothing BD cube. Now here the B will be 100 and D will be 10 upon 12 divided by area is same, 10 into 100. It will be something 2.8 mm. See this. So see this value is high and this value is less. RYY is less. Generally RYY is less. In general I'm talking. Because moment of inertia about y-axis is less. Here you can see IYY is less because this D is very smaller here. Here the D is more. Okay. So that means we can say that your buckling is governed by the R minimum value. So it is governed by minimum value because it is buckling about minimum minor axis. Okay, where the dimension is less, it is buckling at that direction, or where the R value is less, there it is buckling. So ultimately we can conclude that our buckling is depending on length and R, that is radius of gyration. And there is a term which is rather we can say the buckling is defined by a term which is nothing but slenderness ratio. We generally write as a lambda, which is nothing but L effective upon R minimum. So this is nothing but your slenderness ratio. So if you want to calculate permissible stresses in compression member, or if you want to calculate the permissible capacity of compression, you need to consider the slenderness ratio. So you have to calculate the slenderness ratio, and we already know that as slenderness, the more slender, the capacity is less. So if lambda is more, capacity will be less. Yes or no? And if lambda is less, that is slenderness ratio is less, capacity is more. Yes or no? कुछ समझ में आ रहा है?
Sir, I want to ask you.
Okay.
Sir, for this x axis, usually we take horizontal. No, then why we choose x vertical and y horizontal?
Yeah, see, okay, I'll just rotate this. There is no problem in that. We take x horizontal, that is correct. So here I had drawn the sketch like this, so I taken that. Otherwise, you can rotate that. Okay, there is no problem. See, generally, whenever we have a steel table, the x-axis is always horizontal for section. Okay, like this. So I should have actually drawn that. It doesn't matter what you are doing. You should know how to take the axis. Okay, so actually this should have been drawn like this first. So that is the only yes. Actually, I should have drawn it like this only, and then say it as x and say it as a y. Generally, depth is a y. So generally, the x is cutting the depth of the section. It is cutting depth of section. Generally, huh? समझ में आ रहा है? So this is your depth, and it is cutting the depth. So here also you can see in steel table, channel is this is depth, and it is cutting the depth. So x-axis is cutting the depth, half parts कर रहा है depth का. It may be channels, it may be beams like this. See this is x and this is depth. So it is cutting the depth. So that is the actual right way of drawing this. So I have drawn that horizontally, so I did that. Okay. But keep in mind, whatever you are assuming, the axis should be kept like that only. Okay, but generally steel table is like this, cutting the depth, right?
Okay, sir. Okay, thank you.
Now, so lambda is more, means slenderness ratio is more than capacity is less, right? This you understand?
Yes, sir. Yes.
So lambda is more, so, or in other words, we can say if the length is more, we have already seen, sorry, that if the length is more, then the capacity is less. We have already seen that here. See, this length is more, so capacity will be less, and which is we can understand through the this lambda equation. So if the L is more, the lambda will be more, and if the lambda is more, then capacity is less. Or if R minimum is more, capacity ज़्यादा होगा या कम होगा? If this value is more, slenderness ratio will be
Less.
slenderness ratio will be less, and as slenderness is less, capacity is more. So if you want to increase the capacity, if you want to increase the capacity of compression member, what you will do? What to do? So if you want to increase the, either you decrease the length, okay, or increase R minimum. समझ में आ रहा है कुछ? Are you getting? Then and then you can have less slenderness ratio, and then the capacity will be more. So whenever you choose any section, choose a section for which R minimum value is more. Or if you have any, say, sections like this. Now, if I ask you, this capacity of section 3 is more. Let's say L1 is 2 meters. L2 is 3 meters. And L3 is, let's say, 3.5 meters. Okay. Now tell me, if you want to increase the capacity, what can you do for this? Let's say 3 member is there. I know. Now practically there is a member like this, but I want to increase the capacity. कैसे करेंगे? What I told you, either you increase this R value. So whatever R minimum value is there, please increase this. Generally, we can increase by increasing the dimension about which axis. So let's say this is your X axis, and let's say this is your Y axis. So how can you increase the R minimum value? R minimum, all of you know that R minimum is nothing but IYY upon area. And if you want to increase, if you increase IYY, then R minimum will increase. And if you want to increase IYY, then all of you know that BD cube. So you can increase D value, whatever D you are taking. And this D is nothing but this D for RYY calculation. So you can increase these values, IYY value, and you can get more value of the R minimum. Or there is other possibility that you can decrease the length, effective length. And if you want to decrease the length, then I can provide one beam like this here. Okay. If I provide beam like this, and then if this is the case, how will it buckle? This will buckle like this, something like this. Okay. There may be buckling like this curvature, because due to this beam, now it is not buckling like this, cantilever buckling. Okay. So see, in this case, it will buckle like this. Or rather, I would say before beam, how will it buckle before putting any beam? Let's say this will buckle like this kind of cantilever here. And this is buckling due to this more length. Now, if you want to avoid this buckling, or if you want to reduce the buckling, reduce length L3, and you can reduce the length L3 by adding some beams in between the column. So you can tie the column, and once you tie the column, then your buckling will be something like this, maybe. Okay. Now this your effective length is now L effective is this, which is nothing but, let's say, 3.5 divided by 5 means 1.75. Let's say. Now this column will have more capacity than this. क्योंकि इसका L कितना है 2 meters and this L is. So previously we were seeing this member as a lower capacity member. Now we have increased its capacity by reducing length L effective LE. How I did it? I have added one beam here to tie the beam. We can say tie beam. And then L effective is now 1.75 and here it is 2 meters. Now this will have more capacity. Getting? समझ में आया?
Yes, sir.
Yeah, so this is the, we can say, in general philosophy. Now let's see what is meant by L effective. So see, it is not L, whatever I told you, it is L effective. So L effective, have we discussed this before regarding L effective? Okay, in short, we will discuss on L effective. So it is something. So generally the buckling is, or L effective length is something related with the point of contraflexure. So we know that point of contraflexure means zero bending moment. So let's say if we have this, let's say, compression member, and let's say I have a hinge over here, I have a hinge over here, okay, and I am applying compressive force like this. So these are pin or hinge, whatever you say. So there is a compression like this, and this compressive reaction here, okay. So this is a compression member, and as it is a compression member, this will try to buckle. But how will it buckle? It will buckle like this. Previously it was buckling like cantilever because there was no support here. So here there is no support, so it is buckling like a cantilever. But whenever there is a support like hinge support here it is also pinned. Both are pinned, and there is axial force in the member. So due to this will buckle like this. So if this is a pin connection, that means zero moment is here, zero moment is here. So in this kind of case, our L effective is, so let's say this is your L total length. So here in this case, L effective is equal to L only, okay? Because these are the point of contraflexure or zero moment points or pin connections, we can say. So L effective is L here. So if it is L, let's say 2 meters, then it will be L effective is 2 meters. Same. Now take some different example. Let's say both ends are fixed. Now as these are fixed and then we are applying a force, let's say compressive force. So this is a compression member and this will try to buckle like this. So all of you know that the point of contraflexure will be something. So it will not buckle. This is a 90 degree. It will maintain first, and then it will buckle like this from here. Then again here and here, and then again this is straight. So I can say there is a point somewhere here, point of contraflexure something here, okay, where it is changing the direction. So let's say this is your L, which is, let's say, 2 meters. But the point of contraflexure, the L effective is nothing but between these 2 points. Where? So this is your L effective, okay, not 2 meters. So when both ends are fixed, L effective is nothing but 0.65 L. And we have seen this L effective values as per the boundary conditions. So how much will be this value? L effective is 0.65 into 2. Getting? Hello?
Yes, sir.
Yes. So, but and here also you can understand that if you want to reduce L effective value, it is better to have the fixed connections, because if the connections are pin connections, then your L effective value is more. It is nothing but L only. So here the L effective value is 2 meters, and here the L effective value is 1.3 meters. So fixed connections, if you create fixed connection in the structures, then you can reduce L effective value. So there are a lot of ways by which you can reduce the L effective values, either in making it fixed or adding some beam members, tie beams, as we have discussed here, or adding beams like this, tie beams. Then you can reduce L effective, or creating fixed connections. So these are the ways you can handle the slenderness ratio. And these values actually we get it from the IS code. IS 456, we have that in the IS 456. All of you may be knowing this, I think. There is, kahan diya hai wo? I don't remember. Table 28, you see here, effective length for compression members. So if both are fixed, 0.65 L. If one is fixed and other is pin, then 0.8 L. Both are pin, 1 L. So we have seen that. And if they are cantilevers, then it is a 2 L like this. So 2 L means the effective length is double. So let's say if we have this case, let's say this is your case where it is a free at one end and fixed at other end, then L effective value for this kind of problem is 2L. So if this is L, then L effective is 2L, which is very, very, we can say, not acceptable case. So generally don't provide such a connection or member where the cantilever is in compression. Please don't do such kind of cases. So don't put any cantilever in compression. Otherwise, it will buckle very fast, because this L effective is 2L, double L, right? So you get the values of L effective from the IS 456, and then you can use it for the slenderness calculations. So we are finally, why we want L effective? To calculate the slenderness ratio. So L effective and R minimum, you get it from the steel table. Either you get it from steel table if you are using standard sections, or you can calculate. Now we have already seen that if the slenderness ratio is more, capacity is less. That means permissible stresses कम रहेंगे या ज्यादा रहेंगे. So sigma permissible, sigma AC permissible will be less or more in this case. Capacity is less mean sigma AC permissible will be
Yes.
less. And here capacity is more, that means sigma AC permissible is more. So this will be reflected. So the sigma AC permissible depends on lambda, that is slenderness ratio. So you might have seen our IS code 800, IS 800 now. It is for design of members. And if you go in this somewhere, design of compression members. So we have already seen for axial stress in tension, this is design of tension members. We have taken the permissible stress as 0.6 Fy. Okay. And for compression members, The code has given this permissible stress value sigma AC in axial compression. So we know that we have a grade of steel as Fy is 250. So we are dealing with this column only. And this here, this is lambda, means slenderness ratio. As the slenderness ratio goes on increasing, here you will say that the permissible stress is decreasing. Getting this?
Yes, sir.
So here you can see. So if you have slenderness ratio less, then your permissible value is more. See here 150 here for 10. And if you see your slenderness ratio is something 100, then the value is only 80. So yeah, 150 or yeah 80. And that is the importance of slenderness in compression member design. So try to keep slenderness ratio as less as possible from your point of view. And if you can't control, then design for whatever stress is coming from the slenderness. Let's say for your section, the slenderness is 80, then for calculation, for design purpose, take this value as 101 and not 150, like tension member. And code is saying that don't design members whose slenderness ratio is more than 180. So they have given the upper limit for slenderness ratio, that is 180 here. So beyond this, don't use it. It is better to change the section. All of you know that if you want to reduce the slenderness, what can we do? What can we do if you want to reduce the slenderness? Yes.
R minimum.
Reduce L or increase R minimum. Yes. So these are the two choices. So here you can say now. Let's take an example and let's design the compression member. Let's say we have a 1 square rod. So I'm taking simple example for training purpose. You can use this. You can take any section and just, let's say we have a force of 100 kilonewton. And let's say this is your fixed condition. And the height is 2 meters. And the cross-sectional dimension is nothing but 100 mm by 100 mm. Okay. And I am asking you, please design this member. Okay. So this is a compression member, all of you know. What will be the L effective value for this? For fixed condition? 0.65?
Yes, sir.
So it will be 0.65 into L is 2 meters. So
1.30.
So it will be 1.3 meters. Let's convert it in mm. So it will be 1300 mm, right? Now R minimum, see why we are calculating. Finally, we are interested in slenderness ratio. So lambda is nothing but L effective upon R minimum. So how to calculate R minimum?
Under root.
Let's do one thing. Let me change this. एक काम करता हूँ मैं. Instead of square, let's take rectangular size. Let's say it is a rectangular and the dimensions are, let's say this is your 50 mm and this is your 100 mm. Okay. So this is your X axis and this is your Y axis. Now tell me how to calculate R. R minimum is nothing but, is it RYY or RXX? कौन रहेगा minimum?
RYY.
So it will be RYY. will be nothing but I y upon A. So how much is this I y? BD cube. So here in this case, B is nothing but 100
100.
into D cube means 50 cube divided by 12 divided by area is 100 by 50. कितना आएगा?
$14.43.
14.43. Okay. R minimum value. Now what is lambda then? L effective upon R minimum. So L effective is 1300 mm divided by ये 14.43. How much is the number this? Lambda कितना आएगा?
90.
90 slenderness, right? Now we want what is the permissible stress in axial compression from IS 800. So it depends. So corresponding to lambda 90 and Fy 250. So lambda 90, what is the value here? Just go in the table. So this is 250 and this is how much? 90 tha na? The value is 90 here. For 90 lambda, the stress is also 90. So this is different, please, as coincidentally, actually it is coming same. And so you got this value. Now our aim is to check whether this rod can take the 100 kilonewton force, whether it is safe or not. Now how to check? So this is, you got permissible stress actually. That's why we have done this. Now you have to calculate actual stress, sigma AC calculated actual. How to calculate? Compression divided by area provided. So compression कितना है हमारा? 100 है ना? I think 100 kilonewton. So 100 kilonewton, that is in Newton, it will be 10 raised to 3. Area provided is, right? This area is, sorry, 50 by 100. Okay. यहाँ क्या किया मैंने? Right, 50. How much is the value? Sigma AC.
20.
So 20 Newton per mm square is your actual stress, which is less than permissible stress. Now, please see here, we are checking here permissible stress with in tension member. This is very fixed. There is no problem in tension member because there is no buckling possibility in tension member. So the stress in tension is always 150 Newton per mm square. But in compression, there is a buckling possibility. And that's why as per slenderness ratio, the stress values are different. And then we have to compare with this. So this is your design of compression member, we can say. Got this?
Yes, sir.
Now, I ask you one. So let's say we have a truss. And let's say this member is having a compression here. Okay. And this compression value is, let's say, 20 kilonewton. Compression. And I'm asking you, please use tube section now. Tube section. And design this for this 20 kilonewton force. Let's say the height of this vertical member is, let's say 1 meter. Okay. Compression is 20 kilonewton. And use tube section, square tube. So let's me 21. Let's do somewhere here. So in truss member, the compression is कितना लिया था मैंने 10 या 20 kilonewton.
Yes, sir.
Compression is 20 kilonewton. Length is actual length is 1 meter. And design square tube. See, trusses can be in square tube, angles, channels, whatever. There are many possibilities for trusses. Square tube, SHS, square hollow tubes. So this is nothing but square hollow sections. Hollow. You might have seen trusses like this. So they look like this, something like this. If it is a square, then it look like this. ऐसे रहते पता है ना? These are hollow. Here it is a hollow and the steel is here. So this is your steel part. So this is your steel part. Okay. Now we want to design. So we have to design these values. What square size you should choose for this design. Now how to do this design? Please tell. Either you can assume once as a square value, assume some value. So whenever you assume, generally you can start with anything. Let's start with some section. No problem. See, previously what we have done last time, whenever we assume any section, we have what we have did. Area required is what we did in the previous case, tension divided by 0.6 Fy, isn't it? ये लिया था ना हमने?
Yes, sir.
Yes, sir.
But here you know that this value, there is no constant value here, isn't it? There is a problem. This value is not constant in compression. So this
Yes.
is for tension. Here what is happening? Area required is C upon permissible value, which changes with slenderness ratio. So there is a, we can say, I don't know what value should I take, but still from experience, you can start with C divided by some value, let's say 100. I'm assuming, see, this is only assumptions. If it goes wrong, we can check it. If it goes wrong, then you can actually calculate the values. Finally, actual calculation is important. But if you are having some doubt, क्या करेंगे, कितना area लेना है, तो because I'm not sure what to do. You can start 100 or you can say 90. अभी 90 आया था ना हमारा ये problem में. So the value may be depending on 90, 100 भी आ सकती है. I'm not sure. So either you can choose this technique. 100 is a good number. Generally, I choose because if I divide this force, let's say हमारा कितना है force है? 20 है ना? तो आसान जाएगा मुझे calculation के लिए. Just divide by 100. Let's say assumption ये है. So कितना आएगा ये? 200. In centimeter it will be, right? Here rough work. This is only rough work. So I should have area somewhere near 2 cm square. Getting? Yes. So let's choose section with area 2 cm square. So do we have, I think the table is different for this. Oof. The code is different, I think. I'm not sure. For square tube, the code is different, I think. Okay. So better way, let me choose channel section. Forget that. I don't have the code now for square tube. Let's better way. ये नहीं करेंगे. Design channel for truss. Channel for truss member. So my area should be near to 2 cm square for channel. So 2 cm square कौन से channel को है? Okay, ये तो बहुत ही कम है, I think so. So our area requirement is very less. So let's take this value to 9.1 MC75. Okay. So let's try MC75. काम करते हो ये length. Now tell me. Now you got this trial. So what is the first step? Lambda. L effective upon R minimum. What is the L effective? Please tell me. Actual height is 1 meter. What is L effective in trusses?
It is pinned, so same one.
It will be
Same.
same because in truss the connection are pin connections. All connections are in truss. All connections are pin connections, and therefore this L effective is nothing but L. So it is 1 into L divided by R minimum. 1 into means हमारा 1000 है ना अभी, and R minimum you get it from table here. So here you can see here MC75 and R minimum is 1. See, RY is minimum. You can see this is RX is 2.9 and RY is 1.19. So let's take 1.19 cm means 11.9 mm. So what is the value of lambda? Something 95 or something. Okay. Actually निकालना पड़ेगा क्योंकि permissible stress is depending on that. So 1000 divided by 11.9. $84.
4.
Okay, so sigma AC permissible will be from table 84 के लिए कितना रहेगा वो? Check it out. So here it is 18, here it is 90. So it will be between 80 and 90, somewhere between 101 and 90. So let's say 95 in between. Okay, so 95 will be 95 Newton per mm square will be the permissible stress, which we will take it for design. Now, what is the next step? Actual stress. So compression divided by area provided. How much is the compression here? We have compression as 20 kilonewton. So 20 kilonewton in Newton is 20 into 10 raised to 3 divided by area provided. So where we get area provided? Area of this kitna hai? So area of, so let's go into the table, and the area is for MC75 area is 9.1 cm square. So 9.1. So here area is 9.1 cm square. That means 910 na?
Yes, sir.
So 910. कितना आएगा stress?
$22.
Less than 95. Okay. Now there is one question that, see, actual stress is this and permissible is 95. That means whatever you have chosen, this is giving heavy section, isn't it? Because you see, you can even have this value more than 22, near to 90 or something, isn't it? So you can decrease this section, yes or no?
Yes, sir.
Yes, but if you want to choose channel section, then actually channel below this, there is no channel below 75 in practice. So you can have two options, that either, see, 75 is the lowest channel value, or you can choose some different members like square SHS means tubes, which I told you. See, actually tube table is not with me currently. I scored for tubes, but you can have different small size tubes also where you can control these values. So why to unnecessarily waste the steel, isn't it? So you can choose some other sections. So it is safe, but costly. So if you want to reduce the cost, then reduce the section. So to optimize the cost, reduce section. So try some other sections where you can have lesser value of A and R is more, and then you can have this value near to 90 or something, 85, 90 something. So this way you can do the design. So I hope all of you have got this compression member design. It's very simple, but very important.
Sir, so this is the point where we decide we will go for angle or channel or
Yeah,
square
yeah,
like
yes,
that.
yes. So this is one of the points. If there is some issue like costing here, you can choose that. So definitely, finally, the consultant or structural engineer is good when he gives say percentage steel or say tonnage of the steel is less. So in any project, cost is very much important. So if you give less cost, then your design will be selected. Definitely fine. Safety is there. Safety, we are not compromising any safety. But if we use our techniques to reduce the cost like this, now you see these numbers and you know that there is enough margin in this section. That means I'm using unnecessarily costly or heavy section here. Why can't I reduce the section? So here you can control the section by reducing the sections. So see, as a designer, if you are a structural designer and you are saying that follow the steps, get the number and say safe and choose this, it is not the case. Look at the numbers, whether they are okay or not, even though they are safe, then and then you can become structural. And also there is one problem. Let's say now you have, let's say instead of this L as 1 meter, let's say you are having a 3 meter length. Then all of you know that when it is a 3 meter, then L by R will be, yeah, 3000 aega. So this will be into 3. So L by R will be very high. That means this value will be less. So you can reduce the length. ये truss का length reduce कर सकते हैं ना ये 3 meter. Let's say if I ask you to reduce the length of the truss member, vertical member को reduce करना है सब. समझो just example. So this is your vertical member, and if I ask you to reduce the height, how can you reduce the height? Let's say this is your 3 meters, and the slenderness is very high. All of you, how can you reduce the length? कैसे कर सकते हैं? आपको कैसे लगता है?
Providing beam between.
Yeah, you can provide some tie like this. कुछ भी कर सकते हैं. All of you know that if this is a 3 meter vertical, and let's say this is your 3 meters, then diagonal will be also very long, isn't it? So you can have such kind of things. ऐसे कर सकते हैं कुछ. So your diagonal also gets reduced, and your vertical also gets reduced. So you can have some like member like this. So depends. I'm just giving idea whether it is practically feasible or not, that you can judge and take decision. There is no problem. But there has to be some creative approach, value engineering approach. And then value engineering approach is only developed by understanding the concepts of the structural engineering. Then and then you can take decisions. Then in this case, this will buckle something like this. Let's say this is your vertical is compression member. It will buckle like this. If you provide this horizontal member. If you don't provide this horizontal member, then it will buckle like this. So see, that is the importance of the buckling, effective length and all. Okay. Today we will close earlier. Any other questions? Yes, questions?
No, sir.
Sulekha, do you have any questions?
Sir, in concrete sections also, the concept is same, no? This like if we have 4.5 meter or 5 meter floor
Right.
to floor height.
Same. See, you know that in column design, you'll learn that in RCC part. Whenever we design any column, so see, we have learned that only axial force member column last time in the concepts, because we were only looking at the conceptual part. But when there is a compression here, there is a slenderness ratio in compression also. And what happens if there is a long column and short column concept? Long column and short column concept. Instead of R minimum values, there is a concept of L by D ratio, L upon D ratio. Okay. So D is nothing but column this depth. So in what direction it is buckling? Let's say it is buckling in this direction. So you should take this D value, L by D, and L is this length. Okay. So L by D ratio, if your L by D ratio is, let's say it is 10, if it is less than 12, it is a short column. Sorry, here I should. If this value is, let's say 15 and greater than 12, it is a long column. And if L by D is, let's say 10, which is less than 12, it is a short column. Okay. So you can understand it is something related with this dimension. And you know that when the depth increases, moment of inertia increases and R minimum also increases. So they are not taking R values in general in RCC design, but the conceptual part is same. L, it depends on L because slenderness ratio is important, and this D, L by D. So D is also indirectly related with R minimum values, isn't it? Because D is nothing but I. I is nothing but root I upon A, and which is nothing but R. So indirectly they are taking this in RCC. Finally, it is a slenderness. And when it is a long column, what happens? In RCC column, when it is a long column, then all of you know that we get bending moment from the analysis, like ETAB or manual calculation. These are the bending moments of column. Let's say this bending moment is 100 kilonewton. Okay, kilonewton meter. So whenever we design, this value is coming from the analysis. And in long column design, let's say L by D ratio is more than 12. It is a long column. So we need to add additional moments due to slenderness. So whenever we design any column section, M design, M means moment. Design moment is M design, moment from the analysis plus moment due to slenderness. Okay. So it depends. If the slenderness is more, then M due to slenderness will be more. Let's say analysis moment is 100. And if the slenderness moment is coming out to be, let's say 50. So we will design the column section for 150 kilonewton meter. Even though analysis is 100 only, but we take additional moment due to slenderness. So thus we are taking care of the design of long columns or slender columns, we can say. So if you have lower slenderness, then this value will be less. Let's say this was for L equal to 3 meters. If L effective is 3 meters, then additional moment is 50. And if L effective is 1.5 meters, then it will be something 25 only. Getting? So ultimately, in RCC also, it depends on L effective and or slenderness rather, we can say. But they are not taking directly. There are some indirect terms they are using in RCC due to maybe some theoretical, maybe due to some research, I think. But in general, if you are designing any compression member of any material, RCC, steel, wooden, aluminum, whatever materials are available in the market, the philosophy is same. It depends on the slenderness ratio.
Sir, one more thing. This moment we are getting 100 from analysis, right? Then moment due to slenderness also we can get from analysis, or it is
no. We are adding this, so it is we get it from the design approach. In design approach, it comes. It is not from the analysis. See what happens on. Okay, you are asking. Let me go in detail. see, generally in whatever real structures are there, there is a possibility of buckling, not buckling, due to vertical loads. There are vertical loads in the building, and there may be lateral loads if there are there. Then building is getting a sway like this. Okay, building is having sway. Vertical load also there is a sway, little sway. So if the force is shifting here, so there will be P into E. So there is a moment due to sway. So whatever analysis moments are there, analysis moments, M analysis plus this M, we can say eccentricity, ME. So we have to add this, and this we call it as a P delta effect. Okay. But see what is happening, doing the P delta analysis is very, we can say, complex and difficult, and we need softwares for that. And it is an iterative process. Iterative means we need to do a lot of trials, continuous trials till the convergence is there. So these are quite complex terms, mathematical terms, convergence, iteration, and all this. And as it is a complex, whenever there were no softwares, we have developed say IS codes and some theories where you can avoid P delta analysis. So avoid P delta analysis, that is related with slenderness and all, P delta analysis. So if you are avoiding P delta analysis, then you should do something else, isn't it? Because there will be some additional moment like this. So to do something else, the IS code has given certain guidelines, IS 456. The guidelines are given regarding additional moments due to slenderness. That you will learn in the RCC theory in some building, whenever we will start with those sessions. You can read the books also if you want. So this is the, we can say, in general philosophy. So that means we don't get it through analysis. We get it, if you want to get it through analysis, you have to do the P delta analysis. And we generally ignore this. We don't do this unless there is a very high-rise building, and then we, in that case, we can go for this P delta analysis in ETAPS. But general buildings, we don't go in this. Better way, we follow the IS code and we add the additional moments. That's it. Okay, got this point?
Okay, sir. Yes, yes.
Yeah. Now, see, the main aim of this training session is, so actually we are going to start with, from the next sessions, you will start with the ETAP software now, because I hope that basic part is whatever we have learned, it is giving you momentum in learning the civil structural engineering. And now if you read any book, if you read any notes, if you do the software analysis design, if you read any codes, now your understanding is there. Now I hope that it got developed within these sessions, whatever 10-15 sessions are done till in this month. And now you are in a position to understand the structural engineering. That is my aim of this conceptual sessions. And I hope that will help you, and please do that. It doesn't mean that our conceptual sessions are over or our conceptual knowledge is over. It will be there within the sessions, upcoming sessions. It will be continuous. So there is no stop to the conceptual knowledge. But this was the month which is giving you the momentum in structural engineering. So please be consistent, think over the concepts. If you have any questions, you can ask, you can write down the questions in your notebooks or diaries. We can discuss that. You can ask on WhatsApp technical forum group also. We can still discuss on that. And now even start reading on your own also. Slowly you please read books or notes, and then you'll understand the way. Say, for example, I have given you this example that we have to add the moment due to slenderness in RCC column design, which are long columns, let's say. So please read the book, and read the book where the long column design is there, and then you'll understand what I'm trying to say. Okay, because the concepts are clear. Now there is a detailing method. We can say detail procedure is there. So detail procedure, definitely books are the right things to refer those detail things. And there are steps, but whenever you read the steps, you will understand. That is the main aim. So shall we close today?
Oh, yes, sir. Today we had a lot of bulk of information, I think.
Yeah. Okay. So
Thank you, sir. Good
thank
night.
you. Good night.